Hi everyone. So today we're going to look at a very interesting question, and you might have seen certain questions where they ask you to prove that a particular quantity is rational. Now, one of the best examples that come to my mind was a question from RMO in 2019, where I believe they had given certain quantities to be rational, and they had told us that another quantity that proved that this another quantity is also rational. So there have been many problems like this in Math Olympiad contests. I believe a few problems have come in the Pan-African Math Olympiad as well, involving such similar ideas. So today we're going to discuss a slightly more challenging version of that. It's a Putnam problem, and it's going to involve a little bit of trigonometry as well. So yeah, without wasting any time, let's just get right into it. This is the problem number A6 from the Putnam exam in 2018. So last problem on the morning section, and 2018 was a fascinating year for the Putnam. It's probably one of the easier Putnams that we've seen in recent years. So this question is actually quite interesting, and it's quite easy for an A6. And in this video, we're just going to be going through some things that you already know, but we're going to use them in smarter ways, right? We're just going to use it so that we can just get to the result without diving into a lot of complications. And we're going to use them very smartly. So we're going to talk about the cosine law, the addition formula for cosine, book sessions of college mathematics, and of course at the end a simulable charging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what does this say? So it says that suppose A, B, C, D are distinct points, right? So that no three of them are collinear. Show that if the squares of the lengths of the sides AB, AC, AD, BC, BD, and CD are rational numbers, and the quotient of this is also rational. So what they're trying to say is that AB whole squared, AC whole squared, AD whole squared, right? BC whole squared, BD squared, and CD squared. All of these quantities are rational numbers. Q is the symbol for rational number, right? 1, 2, 3, 4, 5, 6. All these 6 quantities are essentially rational numbers. Then we need to prove that the area of triangle ABC divided by the area of triangle ABD is also a rational number. So really all we're going to need is just concepts or just things that you have already studied in basic trigonometry. Okay, so let's try to form one particular configuration of how this might happen. They've explicitly said that ABCD are distinct points so that no three of them are collinear. No three of them can lie on one straight line, basically. So for example, one particular configuration can be, this is A, this is B, C cannot lie on the same line. Let's consider C to be somewhere here, and again let's say D to be somewhere here. Let's say they form something like this. Let me just maybe connect these points. There we go, and let me just draw this line as well. And let me just take this angle as alpha, and let's call this angle as beta. Now what they're telling us that we want to prove that the area of triangle ABC divided by the area of triangle ABD is a rational number. This is what we essentially have to prove. Now what will be the area of triangle ABC? It will be nothing but half times AB times AC times sine alpha, right? Two sides and the included angle. This can be very easily seen via the cross product of vectors, or I'll just draw a very small proof over here of that. So let's say we have this triangle ABC, just any random triangle ABC, and we have this height h over here. Let's say this angle is alpha, just a random configuration. Now what will be the area of this half into base, which is BC, into height? Now if you actually notice, h over AB is sine alpha, or I can write h as AB times sine alpha. Now if I just plug in the value of h over here, I'll see that the area A is equal to half times BC times AB times sine alpha. What does that mean? It essentially means half of two sides, BC and AB, and the included angle alpha, right? That's essentially the idea. So over here in our figure, we'll get the area of triangle ABC to be equal to half times AB times AC and the included angle sine alpha, which you can very clearly verify from the figure. And area of triangle ABD is nothing but half times AB times AD times sine beta. So what we need to prove is that area of triangle ABC divided by area of triangle ABD, this is rational, right? In other words, AC sine alpha divided by AD sine beta, I need to prove that this is rational. I need to prove this. This is where we want to go at the end of the day. Right? So I just need to prove that this is rational. Now what I'm going to do is I'm just going to use cosine law. So if I use cosine law, I can easily write 2AB times AC times cosine alpha. This is equal to AB squared plus AC squared minus BC squared. This is this we can figure out when we apply cosine law in triangle ABC. I'll just write that over here. Similarly, I can write 2AB times AD times cosine beta. This is equal to AB squared plus AD squared minus BD squared. And this can be very easily seen when you apply cosine law in triangle ABD. This is applying cosine law, right? Now, what I can do is I can just maybe construct this line. It's a dotted line. Now, in triangle ACD, if I apply cosine law, I'll get 2AC times AD times cosine alpha plus beta will be equal to AC squared plus AD squared minus CD squared. And this is obviously, like I said, apply cosine law in triangle ACD. So if you actually notice, all I've really done is apply cosine law 3 times. Right? This is the cosine law. Okay, awesome. Now, if you actually notice, the right hand side on each of these expressions is a rational number. Right? Why? Because they've given us the squares of these quantities are rational. AB square, AC square, BC square, all of these things are rational. This is given in the question. And whenever you add or subtract rational quantities, you still get a rational number at the end of the day. So the right hand side is rational. What does that mean? That means that the left hand side is also rational. So let me just write that. So I get 2AB times AC times cosine alpha. Then 2AB times AD times cosine beta. Then 2AC times AD times cosine alpha plus beta. All of these 3 quantities are rational. All of these 3 entities are rational. Like, let's get that very clear. Now, if I square these terms, they'll still be rational. Right? If a particular number, for example, 2AB times AC times cosine alpha, this is rational. Now, if I square it, it will still be rational. Right? So what does that imply? It implies that 4AB squared times AC squared times cosine square alpha is also rational. Now, if you actually notice, 4 is rational, AB square is rational, AC square is rational. That implies cosine square alpha has to be rational. There is no other way. And similarly, cosine square beta has to be rational. And similarly, cosine square alpha plus beta has to be rational. All of these quantities need to be necessarily rational. Right? So I can conclude that cosine square alpha, then cosine square beta, and cosine square alpha plus beta are also rational. But we know that sine square theta is nothing but 1 minus cosine square theta. So basically, sine square alpha will be equal to 1 minus cosine square alpha. Now, if cosine square alpha is rational, 1 is obviously rational. That means that sine square alpha has to be rational, right? Like I said before, if rational numbers are added or subtracted, you at the end of the day still get a rational number. So that means that sine square alpha, sine square beta, and what was the third one? Sine square alpha plus beta is also a rational number. Let me just label that as result number 1. And we will call this as result number 2. So till now, we've got 2 fascinating results, right? First, we kind of received that 2AB times AC times cosine alpha, and actually these 3 entities, all 3 of them are rational numbers. Secondly, we also figured out that sine square alpha, sine square beta, and sine square alpha plus beta, all 3 are rational entities, right? Let's get that very clear. Now, what I'm going to do is I'm just going to analyze this expression. What's that expression? 2AC times AD times cosine alpha plus beta. Because we have this alpha plus beta, we can kind of play around with this a little more than the other 2 expressions, which simply involve alpha and beta, right? This gives us more room for us to kind of expand on what we are doing. So I can write this as 2AC times AD. But now I can use the formula for cosine alpha plus beta. What is it? It is cosine alpha cosine beta minus sine alpha sine beta, right? Now, I can essentially just write this as 2AC times AD times cosine alpha cosine beta minus 2ac times AD times sine alpha sine beta. Right? Okay, awesome. Now, if I just consider, let's say, this expression as k, let me call this entire thing as k. So k is nothing but 2ac times AD times cosine alpha times cosine beta. And this is, let's say, k. Now I'm just going to write k in another way. So I'm going to write this as 2ab times ac times cosine alpha multiplied by 2ab times AD times cosine beta. Now if you actually notice, I added a couple of things. I added an extra 2 over here and I added an extra ab squared over here. Right? So essentially when you divide this, the quotient is still k, right? It's the same quantity. Right? Basically what I did is I introduced this extra quantity 2. I introduced an extra AB, and over here also I introduced an extra AB. All other terms, the 2, the AC cosine alpha and AD cosine beta, were initially in k as well. Right? So to make it equivalent, I divided by 2AB squared. Now do you realize something over here? 2 is rational. AB squared is also rational. This entire quantity is also rational. 2AB times AC times cosine alpha. 2AB times AC times cosine alpha is rational. 2AB times AD times cosine beta is rational. So this is also rational. So that means that k is a rational number. But what was k? K was this quantity, right? 2ac times AD times cosine alpha cosine beta. So 2ac times AD times cosine alpha cosine beta is a rational number. Now let's go back over here. 2ac times AD times cosine alpha plus beta is a rational, right? We know that from this result number 2, right? We know that from here. So the left hand side is rational, the right hand side also has to be rational. What is this? Right hand side is equal to this k, which is also a rational term. That means this thing also needs to be rational because k is rational, right? So that essentially implies that 2ac times AD times sine alpha sine beta also needs to be a rational number, or in other words, I can simply state that AC times AD times sine alpha sine beta is a rational quantity. And if you followed it up till here, doing all those things that we've done, we are basically very close to the solution. Now, just to remind you, what did we have to prove? It's very easy to miss out on what we have to prove. So let me just remind you, we had to prove AC sine alpha divided by AD sine beta is a rational number. But what is this quantity? If this quantity is nothing but the numerator times the denominator, right? So till now we have proved that AC times AD times sine alpha sine beta is a rational number, and this is to prove, right? Now what I'm going to do is I'm just going to divide this by AD squared times sine square beta. It will still be a rational number. It will still be a rational number, right? Because AD whole square is a rational number that we've given in the question, and sine square beta is also a rational number that we just proved, result number 1 that I marked above, right? So essentially this thing is still a rational number because the rational divided by rational is anyways rational. Now what I can do is I can just simplify this. So this AD gets cancelled, sine beta gets cancelled, so you're left with AC sine alpha divided by AD sine beta, and that is a rational number, hence proved. Right? That is essentially what we have to prove. AC sine alpha divided by AD sine beta is a rational number, and we have proved that. So essentially what were we doing this entire while? We're just playing around with the things that we know, right? We're just proving things rational. We're just going around. We started with the squares of the sides, and then we used a little bit of trigonometry, formed the figure, and used the area of the triangle concept, and then we tried to prove that the angles are rational. Sine square alpha, cosine alpha plus beta. We try to prove that cosine alpha, cosine beta times AC times AD. This entire thing is rational. And then we just played around with that a little bit till we got to a desired output. And getting this as rational was very important because if you see this is nothing but the product of the numerator times the denominator of what we need to prove is rational. Right? So this was, I think, a very interesting question. But one thing that you need to keep in mind is this configuration that we had formed. Let me just show it to you. This configuration that we have formed is one particular configuration. The problem with this is in the question they've never told us that ABCD form like a quadrilateral kind of arrangement. Right, so this is one possible structure. What essentially can also happen is that, for example, if we have the triangle ABC like this, point D can lie somewhere over here. in my figure, I kind of assume that point D lies over here. Right? And then the quadrilateral was formed. So point D can lie inside also, right? It's not like bound that point D has to lie outside of it. Right? So basically point D can lie inside also. But the interesting thing is that you get the same result. Right? And the only thing that changes in our entire procedure is, like, you remember we were calculating cosine alpha plus beta. If we have this D inside, you would have cosine alpha minus beta. That is it. That's the only change that will happen. Otherwise, it's essentially just proving the same thing. And cosine alpha minus beta will open as cosine alpha cosine beta plus sine alpha sine beta. We'll just open like this. Otherwise, the entire procedure remains the same. And I want you to try this out. If you've understood what I've done, maybe try proving the case where the point D actually lies inside the triangle ABC. Or in other words, any one of the point lies inside of the other three, and the other three form a triangle. Just by without loss of generality, you can state that. So I think this could be a good way to just kind of get yourself used to the procedure that we use while proving something is rational. So yeah, I really hope you like this question and had fun with it. Okay, so we have certain book sessions of college mathematics, Introduction to Real Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galian, Topics in Algebra by Herstein, Abstract Algebra Dumit and Foote, and of course, Linear Algebra done right by Axler. So we have a similar but challenging problem, and this is probably not as challenging because in the problem that we just discussed, we had to use trigonometry and all. So we had to very kind of cleverly use the trigonometry formula at our disposal so that we can get to the result as quickly as possible, right? But this question is relatively a little bit easier, and this is actually the RMO problem that I was telling you about. I believe this is RMO 2019 problem number 1, and I had given this test myself, and we need to suppose that x is a non-zero real number, so that x is to the power 5 and 20x plus 19 by x are both rational numbers. Prove that x is a rational number. So I think this was a great start to that paper. It was a pretty easy question, and a lot of the people were able to solve it. So I'm pretty sure all you really need to do, there's no new concept involved. The best thing about proving something that is rational is you don't need to learn any new concept whatsoever. You just need to use the things that you know in your toolkit, problem solving toolkit, and just employ them in a smart way so that you get to the answer in a quick manner, in an efficient manner. Right? So maybe try this out, and if you're able to do this, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.